Now we are going to take up a new property, that is the thermal conductivity of solids, right. So you will be surprised to know that when we talk about thermal conductivity of solids, so solids show you can say varied range of the conductivity, right. So that means the conductivity of the solids vary to a great extent, right. So according to the thermal conductivity, we divide substances into three categories, all the solids one, right. That is the conductors, we have semiconductors, and we have insulators, right. So what are actually conductors? Conductors are those which have high conductivity. Semiconductors are those which have moderate conductivity, and insulators are those which are very poor conductor, or you can say their conductivity is too poor, right. So just let's focus on the examples. Conductor, suppose it's copper. Semiconductor, suppose we have silicon, germanium, etc. Insulators like wood, right. So I think it's clear that on the basis of thermal conductivity, or on the basis that whether the substance allow the current to pass through it or not, we have three kind of substances. The one which allow all you can say a high amount of current to pass through it are called as conductors, which allow moderate amount are semiconductors, and which do not allow at all are insulators. Now the question must be fluctuating in your mind that like if I have copper and wood, as we know that both are matter, right. Even copper is matter and wood is matter, and we all know that matter is made up of small particle, that is atom, right. So this must be striking your mind that why copper is a good conductor and but wood is not a good conductor. The reason behind that is the presence of free mobile electrons, that is the free mobile electrons. The one which has these free mobile electrons is good conductor, and the one which doesn't have that free electron is a poor conductor. So likewise, copper has that free electrons and wood is deprived of those free mobile electrons. Now you must be thinking that because they both are matter and both are atom, and we all know that atom contain proton, neutron and electrons. So then what is the reason that the copper possesses that free electrons and wood doesn't have that, right? So I am just going to explain this, and just look at the board carefully. See, suppose I have a copper wire. This is my copper wire. So what do I get to see in it? I get to see that here are many copper atoms in a copper wire. Obviously it is made up of copper metal, that means it must be possessing copper atoms. So let us draw a model of this thing with the nucleus and the shells of copper. So this is what we have here in the wire, means nucleus and many shells of copper atoms like arranged like this, and we have negative terminal of battery and we have positive terminal of battery. Then what is going to happen when we are going to pass current? Then the electron is going to pass here, right? I'll just draw with another color. It will come here, it will jump from here to here, here, this way, this way, this way, and finally it will just pass through that copper atoms, right? So that means copper allow that movement of electron, but wood doesn't allow. Again, our answer is still unanswered, right? Our question is still unanswered, because it must be, you must be thinking that why this can't be seen in the case of wood. So this is explained something on the basis of quantum mechanical model of atom. Quantum mechanical model of atom. So what is actually quantum mechanical model? So what we know that there is a nucleus in center of atom and there are different shells around it. You all know that, right? So this is a nucleus, right, containing proton and neutron, and these are the shells. We also call these shells as levels. And what is present in these shells? You all know that electrons are present in these shells. Electrons are present in these shells, right? So what happens? See, every shell has fixed amount of energy. Every shell has fixed amount of energy. So we can say that these shells are actually energy bands. Correct? So each, again I'm telling you, see we have, the atom structure, nucleus is in center and it is surrounded by the shells, and in shells the electrons are seen, right. So when we talk about the energy, every shell has fixed amount of energy. Every shell has fixed amount of energy. So we can call those shells as energy bands. We can call them as energy bands, right. But if we see that in what order of energy they are arranged, so you should know that the first shell is of low energy, and likewise the energy increase. You all know how to write this configuration, we did in atomic structure as well, right. So that means, suppose I have first shell, so this correspond to 1s, the second one correspond to 2s, 2p, likewise this is 3s, so on, right. So that means my concern is that I just want to convey you this, that the shells which are surrounding the nucleus are actually having the fixed energy, so we can call them as energy band, right. Now when we talk about energy band is categorized into two categories, means we get to see two kind of energy bands. One is valence band and the other is conduction band. One is valence band, other is conduction band. Now we just want to know that what is valence band, what is actually the valence band, or what is the difference between these two bands. So see, we know that this is an atom, right, we know the energy bands. So the last shell of an atom, the last shell, which one is the last one? This one. So this is something called as valence band. As I told you that all shells are actually energy bands, but the last shell is called as valence band, right. So this is the valence band, right. And now what is the conduction band? See, after valence band you don't get to see any kind of shells, but we have also learned that there is no definite you can say the structure of atom. That means the shell may extend up to you can say a great distance, right. So that means there is no confined area of the shells. So it is assumed that there is a fictitious shell outside the valence band. All the shells which are outside the valence band, the fictitious one, the virtual ones, they are something called as conduction bands. I think it's clear, you are clear with the bands, because once you will be clear with the bands, then only you will get to know that what is the reason that some substances are conductors and some are insulators. Again, just listen to me carefully. Shells are called as energy bands, right, because they possess definite amount of energy. Valence band is the one in which the last electron is present, and apart from that, the shells, the virtual shells which are surrounding the valence band is actually the conduction band, right. So this is clear. Now what happens? We know the electron excitation process also. We know the electron excitation process also. What is that? It is like, suppose electron is present here and I supply it energy, and if the energy which I supply to it is greater than the energy of this shell, then the electron is going to jump to higher energy level. We say it gets excited, right. So it stays there for certain time and then definitely it moves back to its shell, and when it moves back it just emits the energy, that is the difference of the energy between those two shells. This is actually called as an excitation process. You know, like Bohr actually explained this process, that whenever we supply energy to an electron and that energy is greater than the energy possessed by the shell, then the electron is going to move from its ground state to the excited state, but the excited state being unstable, it is going to remain there for certain time, and then ultimately it will return to its ground state, and in doing so it will just release the energy absorbed by it, and that is equal to the difference between the energy shells, right. So this is what we have, the excitation process. So this excitation process actually happen in it, right. So what happens, suppose when we supply energy to it, then what happens, if that energy is greater than the energy possessed by the electron in the valence band, if that energy is greater than the energy of the valence band, then only the electron is going to get excited to the conduction band. And when we say it get excited to the conduction band, because conduction band is a virtual band, we say that it is almost free now, that electron almost becomes free and it can move, and this is the reason that some substances have free mobile electrons and some do not, right. The reason is that when we supply energy, so that energy should be greater than the energy of the valence band, right. One thing. then only electron is going to move from that band to the conduction band, and when it is in conduction band it is almost free to move, right. So that means it will now fulfill the criteria of free mobile electrons, and that substance is going to be act as conductor now, right. So this is what happens in any substance when we just want to know that whether the electricity conducts in that given substance or not. Now we will just observe in case of conductor, semiconductor and insulator that what is happening in case of like this phenomena, how it is operating in these things, in these substances, that we get to see high conductivity in conductors, moderate one in semiconductor, and this thing, the poor conductivity in the insulators, right. So just look at the board. Here I am going to do for the conductors. We see for the conductors, suppose this is the valence band, and energy of valence band is suppose EV, right. And when we look for the conduction band, it is not here, it is not here, it is almost overlapping the overlapping the valence band. So there is hardly a difference of energy. So when we supply a little amount of energy, then only the electron get excited from this to here, and when it get excited to the conduction band, it almost becomes free and it is able to move. That means it is able to conduct the electricity, right. So this is what we get to see in conductors. But when we observe this kind of phenomena in insulators, what happen? Suppose this is my valence band and energy of my valence band is EV, right. So we will just look that where that conduction band is present. So conduction band is not overlapping, obviously it is not here. It is all you can say the distance between the valence and the conduction band is at least this much, and the energy which we supply to excite an electron, suppose my electron is here, I am just going to supply it energy. That energy is insufficient. That means it does not cause any kind of excitation because the energy difference is too high. So no such excitation take place, and when no such excitation take place, that means the substance is not going to conduct electricity, and we know that the substance which do not conduct electricity is something insulator, right. So this is what we get to see in insulator. Now semiconductor, what happens in case of semiconductor? Suppose this is my valence band, this is my energy, and this is my conduction band. So conduction band is almost, it is at certain distance but not at too much distance, right. So that means suppose I have 5 electrons here. So when I will supply energy, not all the electrons are going to get excited as it was seen in the conductor one, right. Only the few electron will get that energy and get excited to the conduction band. Suppose I say if I have 5, so one will get out of 5, one will get excited, and one that get excited becomes free and it is able to conduct electricity. So that means the semiconductors conduct electricity but not to a full value, they conduct up to a small amount. That is why we say their conductivity is moderate, because not all the electrons get excited because the energy difference is there, right. It is not too much, it is not too low, but still it is there. So when we supply energy, only few electrons take up that energy and get excited, or you can say become free and they just move. So that means conduction occurs, but it occurs obviously from the, not from the all electrons, it occurs only from from the few ones, right. So this is what we get to see semiconductor. But see what happens, we can actually increase the conductivity of semiconductors. We can actually increase the conductivity of semiconductors. How? First factor is temperature. If we increase the temperature, conductivity of semiconductor just gets increased. And there is one more mode by which we can increase the conductivity, that is the addition of impurity to semiconductor. So this thing is not observed in case of conductor or semiconductor, even in insulator. Like if you supply temperature, then also it is going to remain as poor conductor, its conductivity is not going to affect. But if we increase the temperature in case of semiconductor, so its conductivity is obviously going to increase. And the second factor I told you, that is the addition of impurity. So that means when you add impurity to the semiconductor, its conductivity is affected. And how it is affected? It just gets increased, right? So that means addition of impurity just increase the conductivity of the semiconductor. Now just let's focus on that topic, that how the addition of impurity just increase the conductivity. So how it happens, just look at the board, it's very important. So see, I told you that when we add impurity to a semiconductor, that process is something called as doping. That is called as doping. So what is doping? It is the addition of impurity to semiconductor in order to increase its conductivity. So addition of impurity to a semiconductor in order to increase conductivity is nothing but doping, right? Now what kind of impurity do we add? So we have two kinds of impurity basically which are added to the semiconductors. So the impurities are electron rich and electron deficient. As the name suggests, electron rich, what does it mean? It means that it possesses many electrons, right? It is electron rich, it is not deprived of electrons, it has got more electrons. Electron deficient means it has less electrons, right? It has comparatively less electrons. So just let's see that how doping affects the conductivity of the semiconductor. So what do we have here? Suppose I am taking an example of semiconductor, say silicon. What is the atomic number of the silicon? Yes, it's 14. And configuration? 1s2, 2s2, 2p6, 3s2, 3p2. Right, this is the configuration. So how many electrons do you get to see in last shell? That is 4. So just I am going to draw the figure for the silicon. So we have 3 shells, right? So I am drawing few atoms just to show that how they are connected to each other. Because this is the you can say combination that exists between the solids. So how many electrons? We have 2 electron first shell, 8 electron, and this is the 4 electron, right? Similarly here, same in this case. As we are not concerned with this electrons of the inner shell, we are just concerned with the electrons of the outer shell. But still I am just making it to make you clear. Now what I am going to do, I am just going to show the linkage, that how different silicons are connected by means of electrons. So I am just going to rub this 4 electron and I am going to make the circular figure in order to show the electron. So 4 electron, let's make 4 circles. Similarly here 4 circles indicating the 4 electrons. Similarly here, and same in this case. This is what is there, right? Now as we know that in a crystal the silicon atoms are linked to each other. So they are linked like this combination with this with the lower one, this. See the electrons are actually linked with these neighboring atoms. This is what is there, right? That means they are linked. Now I am going to add electron rich impurity. So let us take electron rich impurity as phosphorus. So how many electrons do we get to see in phosphorus? It is atomic number is 15, so that means configuration is 285. So that means 5 electron in outermost shell, right? So now I am going to add this electron rich impurity to this silicon crystal. So suppose I say that this silicon now gets, I am just going to rub this all, because now it is just replaced by the phosphorus. So this is our phosphorus now. And when we talk about electrons, so it has 5 electrons as I told you. So I am just making 5 electrons. So these are like that. Now how it will get linked? It will get linked with this phosphorus electron with this silicon electron, this phosphorus with this silicon, this phosphorus electron with this silicon, and this phosphorus with silicon. But we are left with this one electron, right? Because all silicon atoms have only 4 electrons, but the phosphorus has 5 electrons. So that means this electron is left behind. This is an extra electron. So what is going to happen? When you are going to apply an electric field, this electron is just going to move under the influence of electric field, and the movement of electric current is something called as electric current, right? So that means it is going to be a good conductor. So this is how you can say that earlier also silicon was conducting electricity, but to a small extent. But when it is replaced by an impurity, when it possesses an impurity phosphorus, so number of those electrons which are free to move just gets increased, because you can see that here is a 5th electron left free. It is not linked to any of the silicon atom. So that means number of free electron just gets increased. So that means the conductivity of semiconductor is increased. So likewise, what we have, like here we add electron rich impurity. Now I am going to add electron deficient impurity. So let's take an example of electron deficient. So let's say boron. Atomic number is 2, 3. That means 2 electron here and 3 electron here, no third shell, right? This is going to happen. So when it is going to replace, we have boron, 1 shell is being removed because it is not present, and what we have in the other electron, we have 3 electrons. So let's make these 3 electrons. So what is going to happen? Again it is going to form the bond. So this electron of boron will form with the neighboring silicon. It will form with the silicon present below, and it is going to form bond with the electron of the silicon present above. But here what we get to see, that here is no electron left with which the silicon can pair up, right? So that means it creates a hole. It creates a hole. So that means this you can say this is now free, and the electron can jump into this hole and just like there is an electron, but here there is nothing. So here will be a hole. Here will be a hole. So that means electrons can jump from this hole, and even this hole can be passed throughout the crystal. That means the conductivity gets increased. So this is how you can increase the conductivity by electron rich impurity or the electron deficient. One more thing, electron when you add the electron rich impurity to a silicon, it becomes the N type, where you get to see an extra electron, and when you get to see a hole, then it is called as P type, right? P type semiconductor. So we have 2 kinds of semiconductor. One is N, which possesses an extra electron, and one is the P type. When you add electron deficient impurity, that leads to the occurrence of hole in the crystal, right? But both of them are just increasing the conductivity. So this is how you are going to comment when you get a question related to the thermal